Good morning, everyone. Welcome to our next class. So today is lecture number 27. So we're not in the book anymore. Right? Uncharted territory. Okay. For next regular class, read 391 to 407. So we're going to have our exam on this coming Monday, and on Friday I'm going to send you a practice exam to do like I normally would, so there won't be a lecture. So the next reading will be for after that exam, right? So on that following Wednesday we'll have a lecture that'll go over the stuff that's on these pages here. Okay. So today is going to be kind of a special class, right? Kind of off the charts a little bit. We're going to go over the ideas of special relativity and of time dilation. Okay. So this isn't part of the real course in mechanics per se. Some professors teach this. I also do, because I think it's one of the more fun and interesting things you can get to in an intro mechanics class. And some textbooks do cover it, though I don't believe ours does in the regular course of the intro mechanics section. So this is something that's not mathematically difficult. It is a little conceptually tricky, and it's quite rewarding, right? You get to see some of the stranger things in physics that you typically wouldn't get to until you got to an upper level class in physics, or if at all, right? If you're an engineering student, a lot of engineering students don't get around to taking these classes. So today we're going to go over some stuff that'll be hopefully really interesting for you guys. And it'll be like a little low pressure, right? This is an advanced topic, even though we can go through all the math just fine. So it's not going to be, something I'm going to test you on directly, either on this upcoming exam or on the final, but it is definitely something that could be a good, extra credit question, right? Oftentimes I do a little relativity extra credit question on either the third exam, which you'll have on Monday, or the final, right? So still good to pay attention, even if you're not like totally psyched about learning special relativity. Okay, so special relativity deals with modern conceptions of time and space. Okay. So if you were here in person instead of just watching me on YouTube, I would ask you, what do you think light is? Okay, and I would pause. So pause, think about what light is, and now I'll tell you. So what light is and was thought to be was controversial for a really long time, right? Our conception of light started in the Middle Ages with the Muslim philosopher, polymath, and some would say physicist Al-Hazain. And Al-Hazain was the first person to develop what's called the camera obscura. So this is something you see usually in your daily life when you look at an eclipse, which obviously doesn't happen so often, but we've had an eclipse a couple years ago, so maybe some of you remember. And a camera obscura is the most, you could call it, primitive form of camera. And what it is basically you have a darkened, empty room or box or something like that. Camera obscura. Right? We have something outside the dark box, say a person. Right? And what the camera obscura does, through this little hole, right? The box or room is closed except for this little hole, is it selects out from each point on this object one particular light ray that has interacted with that object. So if I've got a light source out here, say the sun or any other kind of light source shining on this object, well, each point where the light hits this object, light's going to go in all directions. It's going to come from the sun, bounce off this person's head, and go in every direction, right? But only one of those light rays will go exactly through this little pinhole, right? Same with all the light that hits from over here, and same for all the light that hits from over here, right? And what this does is it basically is a very primitive imaging system, and if I were in this darkened room and I saw, or rather there was someone standing outside or something outside, when I looked on the inside of this box, because of this pinhole, I would see an upside down image on the far wall of that person. So this was invented by that person I mentioned, Alhazen, and was the first sort of optical experiment or optical device, you could say, that was invented. And what you see from this is it looks like, well, light is traveling along these straight lines, right? So people originally thought perhaps light is some sort of invisible particle, right, that's traveling along on these straight lines, right? And because of this pinhole, I can now form this image on the other side. Okay. So in the ancient world, it was oftentimes thought that light was a little particle. The Greeks, ancient Greeks, thought that light was a little tiny piece of elemental fire that could move along straight lines. And this idea that light was a particle was prominent for a really long time, even up until Newton. Newton also thought that light was made up of little particles. There's a really long history of books have been written about this debate between whether is light a particle or is it in fact a wave, right? So there's also reasons for thinking that light is a wave because sometimes it does behave like a wave, right? So if I took an interface between two materials, say I have, I don't know, air on this side and glass on the other, or water or something like this, right? When I have light coming in to that interface, well, it's going to bend as it moves through that interface. So this can't really be explained with the particle theory of light very easily. Now Newton, who was a big fan of the particle theory of light, or what he called the corpuscular theory of light, right? Light being these little objects, little tiny objects called corpuscles. He thought that what was happening was that when this particle interacted with this surface, right, as it interacted with this new material, it sent out waves that moved through this material, and these waves acted back on the particle and changed its trajectory so it looked like this, right? If I thought that light was a wave, it'd be a bit easier to see why this happened, because different parts of the wave are going to interact with this material at different times, right? Because this is going at some angle, so this part of the light wave would hit that material before this part of the light wave, right? And then because light is then traveling at two different speeds in each of these materials, that would cause that light to bend towards the direction of incidence like this. Okay. So this idea of refraction was evidence for the wave theory of light. The light was made up of a wave of something that traveled through air or space or different transparent materials, right? So this debate between is it a particle, is it a wave, went on for a long time. More evidence of, it's a particle, not a wave, might be, well, if I looked through a door, right, I can only see things that are directly in front of the door, or directly behind the door, right? I can't see around the corner. I can, however, hear around corners, right? Because the sound waves move and bounce around and come at me, right? Through the air, and they trickle down or through, and I can receive information about sound, although I can't get the same information if I'm talking about a visible object, light, right? But this all changed with James Clerk Maxwell, who was one of the first people to study mathematically and foundationally the topic of electromagnetism. So Maxwell came up with a series of equations that are now known, of course, as Maxwell's equations, that describe how electromagnetic fields behave, all right? And I'm not going to get too much into the stuff he did, but one major result that came out of his studies was that if you take these equations, Maxwell's equations, you can arrange them in such a way that they have what we call wave-like solutions, right? That they can be rearranged such that we see that there can be an electromagnetic field that propagates as a wave through space. Right? And what pops out of these equations, Maxwell found, was the speed of these waves, which was exactly the speed of light. Right? So this then kind of blew these particle or corpuscular theories out of the water that, hey, we can find material that supports waves, right, in this new way. This electromagnetic field supports these wave-like solutions, and the predicted speed of these waves is exactly the speed of light. So after that, people more came around to the idea that light was not a particle, that it was a wave. Okay, now this is something that could take several classes to talk about and explain. I won't do that, but I just want to impress upon you that around the time of the fin de siècle, around the time of the change from the 1900s to the from the 1800s to the 1900s, people were very much thinking that the wave theory of light was correct. Okay, but there was a problem. Right? If you think about waves, right? Waves always seem to move through a particular material. We hear sound waves because the air is vibrating, right? If we take away that air, I can't have sound, right? There's no sound in space. There's no sound when there's a vacuum. There's only sound when we have this intermediary material to carry those waves, right? Same with water waves. I can look at the ocean or a marina with boats moving around and I can see the waves travel through the water, but that's just because the water's there. If I remove the water and there was just nothing there, then of course I could not have water waves. Speaking of light, I'm having, the brightness is changing. Well, not so much now, maybe. I really need to learn more about audiovisual stuff. Hopefully the changing in brightness as I move around is not too annoying or distracting. But I'm gonna open my blinds actually. Maybe that'll right back. Okay, maybe that's a little better. Hard to tell, but maybe. Okay. Yeah, light waves. So at the turn of the century, people were trying to figure out, well, if light's a wave, what is the material, the medium through which light waves? Right? What is that? So their leading theory was that all of space was filled with this material that they called the luminiferous ether. So if you think we have, the Earth sitting out in space, that space, from the perspective of the theory of the luminiferous ether, it's called ether. Where's my other? That Earth isn't just in this vacuum. There's this invisible substance called the ether that's essentially everywhere. Right? All throughout space, it penetrates all different materials. We have, they thought we have ether inside of us. We have ether in glass because light can go through different materials, right? So if it can go through a material, that means that the stuff, the ether, must also be there. We can see light from space, right? Of course, we can see the light from the sun, which means for that light to get to us, it has to move through this ether, so that ether has to be everywhere in space, right? So this is their theory about how these light waves could be transmitted, right? They had this material, the ether, that allowed the transmission of light waves, just as air allows the transmission of sound waves, for example. But there was a problem, which is, how do you prove the existence of ether, right? Scientists are not content to just say, oh, here's a theory that I've come up with and it seems to make sense, so I'm done. Scientists don't behave that way, and neither should you. You should always be critical, of course, of information you're given and perform your own investigations, and we'll see more evidence for that later in this class. So not content to say, okay, there's this ether stuff, that's what carries electromagnetic radiation, that's what carries light. They said, okay, let's try and prove the existence of the ether. So how would you go about that? Well, here's what they came up with. A reason that, the Earth's not just sitting still in this goo of ether, this sea of ether, right? It's moving around on its orbit around the sun. And everywhere the Earth goes, there's also ether. Okay? Now, as the Earth goes along on this orbit, well, if the ether is everywhere and it's relatively, stable, it's going through all space, etc. If the Earth is moving through this ether, well then, we should see an ether wind blowing opposite the direction of the motion of the Earth. Okay? So, what they did was they constructed a device, which I'm not going to get into how that device worked. If you have further interest, it's called the Michelson-Morley interferometer. Michelson. I'm probably spelling these people's names wrong. Right? But if you spell it vaguely correctly in Google, it'll fix it for you. So they built this device called the Michelson-Morley interferometer, and what the Michelson-Morley interferometer could do was measure the speed of light along particular directions, right? So this device was very large, very heavy. It was built on a stone slab for stability, and then this stone slab was floated in a pool of mercury, so they could rotate this device in any direction they needed to face different ways that they thought the Earth was moving relative to the ether. So, if the Earth is moving this way through the ether, if I shine a light beam this way, well, it's going to be a little slow going forward because I have this headwind of the ether, but on the way back, right, it's going to be sped back up. So, if I'm shining a light into the exact direction of the ether, right, I don't see any difference in the speed of light. However, if I shine that light perpendicular to the direction of the ether, well, there's going to be some slight mismatch, right? Light's not going to go in and out. It's going to be dragged backwards by the current of that ether, so it'll follow a path like this. Right? So it goes out, it comes back in, and now, because it's a triangle and not a straight line, and both directions are vaguely perpendicular to the direction of the wind, right? This extra distance that the light has to travel would make that light going perpendicular to that direction of flow slower. Okay? So they fully expected that they would see evidence of the ether. They did this experiment many times with many variations, and they never found any difference between light traveling in one direction versus another direction, no matter which way they turned it, no matter what time of the year they performed this experiment on. They always saw light traveling at the same velocity for any observer. They never saw any variation on the way light moved. Okay, so this was a big mystery. In fact, it was one of the great unsolved mysteries in physics around the time of the turn of the century, right? The previous turn of the century, from 1800s to 1900s. So this remained a mystery for a while, and people came up with all these possible explanations for why it might be that this variation was never seen in any of these experiments. People thought, well, perhaps the Earth drags a glob of ether around with it. Maybe ether sticks to the Earth and this and that, and they're coming up with all these other theories. Well, none of this research really went anywhere until Albert Einstein, doing sort of a separate investigation into electromagnetism and some of the inconsistencies that were there in the base level of the theory, Einstein came up with the idea that perhaps light travels at the same velocity for all observers. Light, of course, travels really fast. It travels about 3 times 10 to the 8th meters per second, which is far faster than any human being could perceive. So it might seem a little strange to say that that velocity is the same for all observers because it's so difficult to tell the difference. But you can tell the difference. You can build a very advanced device like that interferometer I was talking about. And what Einstein was saying is of course you didn't see any variation on the speed of light because my theories are starting to suggest that light should be moving at the same velocity regardless of observers. So why is this strange? It means that if I'm standing in the side of the road, right, and I blink a flashlight at a wall, right, and send a light pulse out to that wall and it reflects back, I see one velocity of that light moving, right? Whereas if someone's driving past me in a car, right, somehow when they're moving past on their car, they don't see their velocity plus or minus the velocity of light. From my perspective, they see the same velocity of light that I do, even if they are in motion or I'm in motion, right? So just think about that for a little bit and why it seems strange, right? We know from Galilean relativity and frames of reference, which we studied earlier in the semester and has come up periodically since then, that our classical understanding of velocities is that they add or subtract depending on whether we're in a reference frame or not, an inertial reference frame, right? If I'm traveling down the freeway in a car at 30 miles per hour and someone passes me going 60, it looks to me like they're going 30 miles per hour. So I subtract my 30 miles per hour from their 60 miles per hour. Likewise, if they were coming at me at 60 miles per hour, I would add my 30 miles per hour to their 60 miles per hour, and they would look like they were going 90 miles per hour. Now for light, none of that happens. Every observer sees the same speed of light. Okay. So what does this mean? Well, what it means is that something fishy is happening with our concept of time. Okay. So again, if you were here in person, I would ask you, what do you think time is? And pause, think about it, come up with an answer, right? Maybe your answer is right, maybe it isn't. In fact, the best answer for this question, what is time, is kind of flip, because our best answer is that time is what clocks measure. Right? It sounds stupid, but it's what we would call in physics an operational definition, defining something in terms of what we observe it to do. So we observe a clock, we see that it ticks, 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 and that cyclical, I don't want to say motion, but that cycle, that periodic cycle, is what defines time for us, right? If we go back to ancient man, they had ways of defining time in the way the sun moved and the way the moon moved, right? When people started building clocks for the first time, they did things like make a sundial that was the same, just charted the cycles of the astronomical objects of the sun and moon. They built clocks that were water dripping, right, periodically from a hole in a bucket. They built clocks that were candles that burned at a certain rate, all kinds of stuff like that. So all of those different kinds of clocks are doing the same thing. They're defining time, right? And in fact, even in our most advanced understanding of physics, we do not have a better definition than that, right? Time is what clocks measure. So, since we're talking about light and talking about time, and how we can make sense of this strange statement that light travels at the same velocity for all observers, we're going to make the most basic definition of a clock that we can think of, which is a clock that uses light, a light clock. Okay, so how does one build a light clock? Well, physically it would be very difficult, if not impossible, but conceptually it's quite easy. Right? We imagine we have two mirrors. Mirror. Mirror. And somehow we trap between those two mirrors a single pulse of light. And all this light does all day, every day, forever, is just bounce back and forth between these two mirrors. Right? The light's completely perpendicular to the mirrors. None of it escapes. Right? It just bounce, back and forth, back and forth, back and forth. Okay. So for our light clock, one tick equals one round trip. Okay, so we're not measuring time in seconds anymore. Okay, we're measuring it in ticks, and we define one tick of the light clock to be it going doot doot, one tick, doot doot, two ticks, doot doot, three ticks. Okay, that's all well and good. But now, what happened? Oh, one more equation. Well, I'll write it. No, I'll write it now. and then I'll write it again later. So 1 tick of our light clock, right, T naught, or rather we'll just say T for now, is going to be 2 L naught divided by C. Okay? So how many ticks we have is this distance, L naught, times 2 because it's, it goes up and down. So that's where the 2 comes from. So that distance divided by the speed of light is our tick for this light clock. Okay. And remember this statement, light travels at the same velocity for all observers. So like I said, that's all well and good. But what happens when we decide to have 2 clocks and synchronize them? Okay. Well, we put them next to each other, see how long they take, maybe adjust the distance of those mirrors, and I synchronize those clocks. Okay? But now what happens if I want to synchronize clocks that are in motion relative to each other? So what happens if I say, I'm waiting here on Earth. Okay, that's Earth. This is me, or you. And I've got a light clock here. I measure out some time. And then I imagine, well, I've got a friend. He's in a spaceship. With a big window in it. And he also has a light clock. Okay. So now we want to figure out, can we synchronize these 2 clocks? One stationary with me on the Earth, and the other moving at some constant velocity v. All right. What will this light clock look like to this observer? Okay. Well, I wish I had more board space. Well, from this person's perspective, this light isn't just bouncing up and down like this. It's going at some angle because the ship itself is in motion. Right? To the person on the ship, the light clock looks stationary. But for the person on the Earth, the light clock is in motion, and therefore the light's not in motion just in this direction, but also in that direction. So from this person's perspective, this clock, or rather the light in that clock, is following some trajectory that looks like this, like a sawtooth. Right? Bouncing not up and down, but like this, as it goes through space. Okay. So let's analyze the geometry of that situation. How am I doing on time? This class might go a little over. But it's fun, so hopefully you don't mind. Fun. So what does the geometry of this look like? Well, this is, I'll draw it in red. You've got that light pulse bouncing back and forth between those 2 mirrors. As the ship travels through space perpendicular to the direction of the light clock. Okay. What does this distance the light has traveled look to us who are stationary on the Earth? Well, we can just use our Pythagoras' theorem. We know that this distance here, that's that L naught. Remember, we've synchronized our clocks, right? So that distance between the 2 mirrors is the same. So if those 2 clocks are stationary next to each other, they'll tick at the same rate. So this L naught has been calibrated to be the same, right? And then this distance here, this is going to be the velocity of the spaceship 1/2, 1 tick of the stationary observer's clock. So the little O, the little naught is for the stationary observer, okay? The person who thinks they're not moving, right? Okay. So this is our velocity that we observe of the ship, okay? And then this is how much time elapses for a half tick, right? So we're looking at this distance here, not this distance here. So that's going to be half one tick from our perspective. So this total distance is going to be the velocity of the ship times a half tick, both from our perspective. Okay. Now it's important to point out, and you know I'll keep mentioning this, that to the person on the ship, it looks like the person on the Earth is moving, right? For that same idea of even classical relativity, okay? If I'm on the freeway and I'm going 30 miles per hour and the person in front of me is going 30 miles per hour, well, it doesn't look like either of us is moving from a perspective on or in the car, right? Someone on the other side of the road would both see us moving or see us both moving at 30 miles per hour. Likewise, if I'm driving down